Hey, and welcome back. So we're going to look at some chemical bonds here, and we're going to see if we can tell whether they're polar or not. And let's go ahead and look at a bond like CC, and let's figure out its difference in electronegativity. So I'm going to write underneath its difference, and I'm going to write En for electronegativity. And what it's going to be is it's going to be the value of carbon's electronegativity minus the value of carbon's. And on the last slide, we said carbon has an electronegativity of 2.5. Now, what exactly do I mean by these lines here? These lines here basically say ignore the plus or the minus, just write down the number itself. So this difference here comes out, of course, to be 0. So there is no difference at all. So what does that mean? That means it is a non-polar covalent bond. So it's non-polar. Sometimes people call this pure covalent. If I can spell. It's a non-polar covalent bond or a pure covalent bond. I'm so sorry about that. What happens if we go to something like CH? If we calculate the difference in electronegativity here, so that's equal to, let's go ahead and set that up. So carbon is 2.5, hydrogen is 2.1. So you should probably have those values memorized. So 2.5 minus 2.4 is 0.4. But whether it was minus 0.4 or positive 0.4, right, we'd ignore that when we wrote that out. So it's 0.4. So it's polar covalent then, I suppose. So polar covalent bond, right? And so on. So we can go on down to something like CO, and maybe something like CF, and we can calculate the differences there. In fact, maybe you can just pause the video and calculate them, and we can compare notes. All right, so let's see, what'd you get? So carbon is 2.5, and oxygen is 3.5. Remember, it's the second most electronegative atom there is, and that difference is -1, but remember, we take the absolute value, so it's 1.0. And again, if we take CF there, so let's see, C and F, so C is 2.5, F is 4. Remember, it is the absolute most electronegative atom there is. That difference is 1.5. So these are also polar covalent. All right, so there you go. So clearly, the bigger the difference, the more polar the bond is. So I always like to think about these as, you know, those little fridge magnets you get, and you get them in the mail from your bank, and they can barely stick to your mail, or stick to your refrigerator, I'm sorry. They're very, very weak, right? So, and you get those magnets, right, that they're a little bit sturdier. They're made of some inert crazy metal, right? So they're a little bit stronger. And then you get the ones that can literally rip nails out of the floor and stick to the fridge so tightly you can barely pull them off. So as you go more and more to the right, a bigger and bigger difference, you have a bigger and bigger electronegativity difference. And if I go ahead and I put the positive and negatives on here, so again, they're both exactly the same electronegativity, so there's no positive and negative end. But out of this one here, carbon's electronegativity is 2.5, and that's bigger than hydrogen, so it's going to have a slight negative and a slight positive, right? We can draw a dipole that points towards the negative away from the positive. And the bigger the difference, the bigger the dipole I'm going to draw here. So that's a very small, wimpy dipole there. Now, if you look at the CO, the more electronegative atom, right, is the oxygen with its 3.5. So the oxygen now is going to be the negative end, and the carbon's going to be the positive end. And if you go all the way to the right to CF, the fluorine, right, is the negative end, and the carbon is the positive end. And I'm going to draw my delta symbols a little bit bigger when there's a bigger difference, and a little bit smaller when there's a smaller, just because I'm a sucker for this. And we can draw the dipole moment arrows in, so it's going to point in this structure here towards the oxygen, and again towards the fluorine, the more electronegative atom. But the bigger the difference in electronegativity, the bigger the arrow, the longer it's going to be, and so on. So if you were smart, right, you would make it 1 centimeter per difference, and that would give you a much better quantitative way to draw these arrows in. So there we go. Now, the only problem is, if we go to a bond like, what's a good one? Maybe sodium and chlorine. So sodium and chlorine, right? And we look up the differences in electronegativity. So sodium is 0.9 and chlorine is 3.0, right? It's the third most electronegative atom there is. If we calculate the difference, we had a difference of 2.1. That's a very great big whopping difference here. But if you remember, that's a metal, that's a non-metal, so it's probably not a molecule actually. It's actually the classic example of an ionic compound. And so if you remember in an ionic compound, it's not a slight positive and a slight negative, it's a full-on negative and a full-on positive. So sodium is actually positive, chlorine is actually negative. So that electron pair, if you like, is being pulled so close to chlorine, essentially it's no longer being shared. It's just completely on the chlorine, and so it's got the negative charge, and since it was pulled away from sodium, it's got the full-on positive charge. So we have to be a little bit more careful with this. So let me go to a new slide and explain. So we're going to calculate the difference in electronegativity, and we're going to apply kind of a cutoff here. So it's relatively arbitrary, but we're going to go ahead and say that if the difference is 0, clearly that is nonpolar covalent, or if you like, pure covalent. So both atoms pull equally hard, right? So an example of something like that would be something like H2 or F2, right? If both atoms are the same, then it's got to be that case, or something like Br2. Okay, now what you do, right, is if you find when the difference is greater than, say, 2.0, and you can kind of argue for 1.7 or 1.8 or 1.9 or 2.1, but I like 2.0 because it's a very easy number to remember. So what you find is that when the difference is that large, essentially the more electronegative atom has pulled the electrons away from the less electronegative. So that is actually in the region that I would call ionic. And an example of something like that is something we just looked at. So sodium chloride or something like lithium fluoride. So these have a whopping great big electronegativity difference. So it's clear that they are full-on positive negatives, positive negative kind of things here. And again, the 2 is fairly arbitrary. So less than 2, we're going to say it is polar covalent. And an example of things like that would be something like the CO bond or the CF bond, let's say. So CO is a difference of 1.0, CF is a difference of 1.5. So they're relatively polar, right? We can go ahead and we can draw the dipole moments in. So they would look something like that and something like that. So CF is more polar than CO. And we saw earlier that the CH bond had a difference of about 0.4. And what we're going to go ahead and we're going to do is we're going to say, and the scale is not to scale, we're going to say that as long as you're kind of 0.4 lower, we're going to say that essentially you are nonpolar covalent. So why is that, right? Isn't it polar? Yeah, it is ever so slightly, right? But the carbon there has got an ever so itsy bitsy negative charge. The hydrogen is ever so itsy bitsy positive. The dipole moment is ever so itsy bitsy pointing towards the carbon. What we're going to say, though, is that that is so wimpy polar. We're just going to ignore it. That's like the magnet that can barely hold itself up to the fridge. Or that's like your boss saying, oh, you've worked so hard this year, I'm going to give you a 0.4 cents an hour raise. And you're like, why did you bother? So I don't really care. So it is so tiny that we're just going to agree that this cutoff is essentially the difference between polar and nonpolar.